I'm going to start this video with number 21 on page 23. It says a 6 kilogram cart starting from rest. So the initial velocity is 0, which means it has no kinetic energy when it first starts. It's pushed with a force of 12 newtons over a distance of 4 meters on leveled ground. So we're not on a horizontal surface. So there is no change in gravitational potential energy. So to find the kinetic energy in the beginning, basically that's 0 joules because you started from rest. The work done, you just have to do the FD cosine theta formula. Now, the direction of travel and the force make an angle of 0 degrees. So cosine of 0 is 1. So this is going to be basically 12 times 4. And that should be 48 joules. And the final kinetic energy. Now, if we do the work-energy theorem, the energy in the beginning plus any work done in between the initial and the final stage should be equal to the energy final. So you started with 0 here. Your work is 48, so your final kinetic energy is 48 because you don't have any other forms of energy. The final speed, well, the kinetic energy final is half mv final square. So this is 48 equals 1/2 times 6 times vf square. And you can do the math and get your velocity. For number 22, a 60 Newton force is applied to a 12 kilogram cart that was initially at rest for a distance of 3 meters on level ground again. The kinetic energy, we're starting from rest. This is kind of similar to the previous one. The work done, you would use the same formula. It would be 60 times 3, so 60 joules. The final kinetic energy, again, you do the work-energy theorem, and you're going to find that the final kinetic energy is basically 60 joules. And the final speed, well, you set this equal to 1/2 mv square. So it would be 120 divided by 12, so it's 10. So VF is going to be a radical 10. And you can put that in your calculator. It's probably about 3.16, I think. Okay. Okay, number 23. A 40 kilogram ice skater going at 8 meters per second slows down using a force of 56 newtons for 10 meters. What is the initial kinetic energy? Now, the initial kinetic energy is 1/2 m, the initial velocity square. That's 1/2 times 40 times 8 square. And that should be 5 times 64. So, no, 5. 20 times 64. Okay. So it looks like 120. It looks like it's 1280. Yeah, 1280 joules. The work done, work equals force times displacement. Now, they're slowing down, which means the force is going back and they're still moving forward. So there's an angle of 180 degrees between the two. So the work is going to be 56 times 10 times -1. So it's negative 560 joules. What is the final kinetic energy? So since this is on a, it doesn't say that it's going up a hill or down a hill. So we're going to assume that it's on a level ground. So the kinetic energy initial plus any work done on the ice skater equals the kinetic energy final. So that's the work-energy theorem. So this is 1280 minus 560 equals the final kinetic energy. Just want to get the answer key. So that's going to be 720 joules. Now to find the final velocity, just write the kinetic energy formula. Okay, so 720 equals 1/2 times 40 times VF square. So that's going to be 720 over 20, so that's 36, I think. So VF is 6 meters per second. So let's make sure this, yep, that's it. Okay, number 24. A 6 kilogram rocket moving at 5 meters per second fires a 25 Newton thruster at a speed of 10 meters per second. What is the kinetic energy initial? So the initial kinetic energy, you have to write the formula, and it's 1/2 mass times velocity square. So that's going to be 25 times 3, so 75 joules. What is the final kinetic energy? Now it's going to be 1/2 times 6 times 10 square. Or you can just do this conceptually. When the velocity doubles, the kinetic energy will quadruple. Okay, so it would be 300. So let's see if the math gives us that. So this is 3 times 100, so it's 300. If you want to explain it conceptually, you could do that. Okay, how much work must have been done? So work is, we're going to do the work because I don't know the distance traveled, so I'm going to do energy initial plus external work equals energy final. Yeah, so the energy we have in the beginning is 75 joules plus any external work equals energy final, which is 300. So this is going to be 225 joules. So that's the external work. For what distance was the force acting? Well, we're going to do work equals FD cosine of 0 in this case, because the force is and the direction of travel have an angle of 0 degree between them. So this is 225 equals the force of 25 times D. So if we do the division here, we should get 9 meters. Yeah, it should be 9 meters. Okay. Again, all these problems rely on the work-energy theorem to be solved. Okay, it takes some practice, and they are not that bad. Okay. So you're given this picture here. If the 120 kilogram cart has a velocity of 15 meters per second at point B, in other words, it doesn't start from rest, how fast is the car going at point D? Well, again, we're going to assume that this surface is frictionless because it doesn't say anything about friction. So we're going to say this is our initial state and this is our final state. So the energy at B, so I'm going to call that energy at B plus any work done between B and D equals energy at D. Now at point B, you have mgh, you have gravitational potential energy, and you have kinetic energy. There is no work done in between, equals, at the very bottom, if I choose this line as my reference for gravitational potential energy, I only have kinetic energy at the bottom. So it's 1/2 mvd squared. I think we can divide everything by mass. This is going to be 10 times 20, so this is 200 plus 1/2 times 15 squared equals 1/2 times Vd squared, which gives us a Vd equal 25 meters per second. Okay, so this is part A. Part B, how fast is the car going at point E? So if the radius here is 6, so this whole distance here is 13, so this is just a distraction here. Okay, I guess this is 1 meter above the ground. So I think we're going to pick, I mean, you got a couple options here. You can pick B as your initial state and an E as your final state, and you can go between D and E. I'll leave that up to you. So just to be different than the packet, in the packet I went between D and E. I'm going to go between B and E. So at point B, I have mg, the height of B, plus 1/2 m, the velocity at B squared, equals mg, the height at point E with respect to this line here, plus 1/2 m VE squared. Now, if I have a choice, I will use point D and E, because in point D, because at point D, you only have one form of energy. So you only have 3 terms in this equation. So you cross this out, divide by the mass, and you have everything you need, and the velocity at point E is going to be 19.10 meters per second. Now at point C, now it gets here and it travels a certain distance, D, and it comes to a stop. Okay? Now, if we choose this point here, the energy here is all kinetic. So it's kind of like this point here is similar to point D, basically. Okay? So I'm going to say the energy at this point here, I guess I can call it F. So it's going to be 1/2 m VF squared, which is really the same thing as D, plus any work that's done over this distance here equals, that's external work, equals, at the end, I'm really not going to have anything. It's 0. Okay? So I think we have the 1/2 m VD squared. The external work is the work done by friction, so it's the force of friction times that distance, cosine of 180, because the force is going back and you're moving forward. And you can solve that equation, and you can find the force of friction, because you have the distance as being 30 meters.
Please tell me.
You are in it.
I always wanted to be in one of your videos.
Okay, you are in it. We're on number 26. Okay. Problems like this are considered to be easy. So you have a mass that's 10 kilograms. It starts from rest, and the surface is frictionless. Okay, so we're going to try to find the potential energy, kinetic energy, speed, and total energy at each level. Now, keep in mind that the total energy has to remain the same. Okay, so that's going to be a constant. And let's try to find the potential energy at point A. And I'm only going to do it for maybe point A and B, and you can figure out the rest. So at point A, you have mgh, so it's basically 10 times g times h, which is basically the elevation above this level here, which I will consider 0 for gravitational potential energy. And that's going to be 4,500 joules. Okay? Now, the total energy here will also be 4,500 joules, because the kinetic energy at point A is 0. So basically, these two numbers here should add up to that last number. Now, the velocity at A is 0 meters per second, because you're not moving. At point B, your elevation is only 40 meters. So it's basically mg times 40. So that's going to be 4,000 joules. Now, your total is 4,500. 4,000 of it is gravitational potential. There is no friction. So the difference is going to be your kinetic. Now, how do you find the velocity at B? You just do 1/2 times m v squared equals 500. So V equals, what is that? It's going to be 10 meters per second, right? So this is going to be 10 meters per second. And all these numbers will be 4,500s. And you can do the same reasoning for point C and D. At point D, you will have no potential energy, and all your energy will be in the form of kinetic, and you know what to do from there. All right. Now let's look at number 27. Just want to make sure we're still recording. Yeah, we're good. Okay, so let's look at 27. For 27, I'm going to pick this level here as my 0 for gravitational potential energy. And really, you can pick whatever you want. You can pick the point where this is going to be after it moves 1.6 meters. I'll leave that up to you. But I'm going to pick this point here. It's just a choice that I made. You don't have to follow that, my choice. So 0 gravitational potential energy here. That's my reference. Okay. Okay, now we need to find the speed of the crates after they have moved 1.6 meters starting from rest. So I'm going to pick my system to be Earth and the 2 crates. Okay, so let's see if we can write the work-energy theorem here. Initial energy plus any work done by external forces equals energy later. Now the only work done by external forces here is the work done by friction. So I'm going to change this to work done by friction. Okay. Now friction is only acting here. So this block is gonna move up to here, and this one is gonna move down to here, let's say, right? So this one will go 1.6 meters here. This one will go 1.6 meters there. Okay. When we're at this level here, I think we start. So let me just write all kinds of energy: gravitational initial plus kinetic initial plus the work done by friction, which is really force of friction times this distance traveled here, which is really 1.6 cosine of 180. So I'm going to put a minus here to reflect the cosine of 180 equals a UG final plus kinetic energy final. So based on this reference that I picked, both of these are 0. All right. Okay. So the force of friction, that's going to be mu. Okay, mu, I think, which is given. Mu mg cosine of 30, because ff is mu fn, which is mu mg cosine of 30, because this is your fn basically. Okay, so I did that, cosine of 30 times the 1.6. Okay, that's the distance over which the friction is acting, equals. Now I have to find the gravitational potential energy for each block. Okay, so I'll do that on the side here. So let's concentrate on this one here. Now, okay, so that one is going to have it's mgh, but I'm going below the reference, so I need to put a negative here. So this is going to be just negative 240, yeah, 240 times 1.6, and that should give me. I should have that somewhere in here, but I can calculate that. Okay. I could actually have done. I could have just left the mg's. Probably they're going to cross out. Yeah, maybe I should just do that. This way I end up with less math. I'm going to put the mg here, and I'm going to keep this as mg. It's probably easier. Okay. Yep. Yeah. Okay. Now let's do the gravitational potential energy when you are up here. So it's going to be a positive, but you have to look at this height basically. That's your new height. So it's going to be mg, same mass, and it's a positive. Now the height of this angle here is 30 degrees, right? The height of this is 1.6 sine of 30, which is basically 0.8. Okay. So now this gravitational potential energy of the system afterwards is just going to be the combination of these two, which basically looks like negative 0.8 mg plus, this is where you have to be careful, the kinetic energy of the system. Now keep in mind that both objects are moving. They have to be moving at the same speed. So the kinetic energy for one of them is 1/2 mv squared. But you have to deal with two of them, and that's key. We have to see that. So I think we can get rid of the masses, right? And if we do the math here, we should get, what should we get? Should get 1.92 for the velocity, 1.92 meters per second. All right, let's look at this problem here. Now for this one here, it doesn't matter how we throw the ball as long as we throw it with the same speed, whether it's up or down. Now don't confuse this with the time that they're going to stay in the air. Okay? The time that they're going to stay in the air is basically C is going to stay the least amount of time, then B, then A. But the velocity down here will be the same because they start with the same kinetic energy up here. They start with the same potential energy up here, okay? And they have to end up with that same amount of energy when they hit the ground. And when they hit the ground, all that energy is converted into kinetic. So, and since the balls are, the mass doesn't matter, it's going to cross out. So they're going to hit at the same level, so they have to have the same speed. If they were different masses, okay, they will still have the same speed, but the heavier one will have more kinetic energy. So difference between kinetic energy and speed. Okay, I think I proved this equation to you in the previous video, so I'm not going to do it again. Okay, so here what I'm going to talk about, let's just say we take so let's just find the V, escape velocity for Earth. And I think we did this in gravitation, and I think we came up with, I think 11,200. Let's say if we fire it at that speed or higher, it will just lose it. This is the radius of the Earth. And you do the square root of this. So I'm going to do it quick. So it's 2 times 6.67. It's 10 to the negative 11 times the mass of the Earth, which is 6 times 10 to the 24th. Divide everything by 6.4, 10 to the 6th, and you take the square root of that, and we should get 11183.13 meters per second, which is about 11.18 kilometers per second. So I think we said 11.2 when we talked about gravitation, so that's close. Now, if we take a different planet, so this is V escape, okay? If we take a different planet that has a mass, I don't know, maybe 2 times the mass of the Earth, you can see that the escape velocity on this other planet will be the escape velocity on Earth times radical 2, because it's stuck with a radical 2 in there that has to come out, okay? Let's say this planet has the 2 times the mass of the Earth, and the radius of this planet is, let's just say, 4 times the radius of the Earth. So let's see what it looks like. So it's going to be 2g. Mass of the planet will be 2 me over 4 re, right? And you take a radical. So you take you leave everything that's common. So everything that I'm circling now with the radical is basically the escape velocity on Earth. So if I take, so this is going to be a radical 2 over 2 V escape for Earth. Right? That's what it is. Yep. Okay. Okay. Number 28. A combined mass of sled and rider is 112 kilograms. The hill is 44 vertical meters high and not frictionless, so basically there is friction. The sled and rider travel 88 meters along the hill and reach the bottom traveling at 19 meters per second. All right, So let's try this. So here's the hill. Actually, if this were frictionless, they will reach the bottom at a higher speed. So they're starting from up here, and they're getting down to here. So this height here is 44 meters. Now, sometimes you will be given the length of the ramp, and you will be given the angle, and you'll have to figure out the height yourself. So the potential energy at the top is just going to be mgh. And that's going to be 112 with a 0 times 44. And I'm getting 49280 joules. Okay. Kinetic energy at the bottom. So kinetic energy. Now, again, we considering the lowest point as the reference in this case. Kinetic energy at the bottom, K, yeah, equals 1/2 m v square, which is 19. So that should give us 20216 joules. Okay. The work done by friction. Now we're going to use the Work-Energy Theorem, right? At the top, the only form of energy I have is UG. Okay? So UG at the top. There's no kinetic energy at the top, but there is some friction between the top and the bottom. So there is some work done by that force of friction. Equals the only energy you have at the bottom is kinetic energy at the bottom. So you can see that the work done by friction is the difference of these two, which is going to be negative 5096. And you expect it to be negative because friction will do negative work. You're sliding down the ramp, friction is going up the ramp. Now, try to find the force of friction, or I would just say the work done by friction is the force of friction times the distance traveled along the ramp, cosine of 180. You cannot forget that. Okay? Now, you have this number. Cosine of 180 is negative 1. And I think we have the length of the ramp, which is 88 meters. You plug that in for D, and you can find the force. And that should be 1820. If you come up with the negative, you probably forgot the cosine of 180. So you go back and fix it. Okay, let's look at 29. Okay, a 98 kilogram sled and rider are traveling at 12 meters per second on level ground. The sled begins to rise up a hill that is quite slushy and generates a bit of friction. Okay, so basically we're like this. Okay, so at the bottom here, the velocity is 12 meters per second. Okay, so here we're going to go, they're going to move a distance of 2 meters in height. Okay, so now we need to find the K at the bottom. Okay, so I'm going to consider the bottom as the reference for gravitational potential energy. So that's going to be just 1/2 mv squared. So it's 1/2 times 98 times 12 squared. And that should give us I think in the previous problem, the numbers that I write to you for the work done by friction were from 29. So for the previous problem, if you go back, the work done by friction is negative 290,064 joules. Sorry about that. Okay. Kinetic energy is 7056 joules. Yeah. Gravitational potential energy at this point here is just going to be your mgh, which is 980 times 2, which is, I think, 1960 joules. Okay. Okay. The work done by friction, so you have your kinetic energy down there at the bottom, plus the work done by friction between the bottom of the hill and the top of the hill equals the only energy you have at the top is gravitational. So basically, the work done by friction is the difference of those two, which should be negative, right? So 1960 minus 7,056, and we should get negative 5096 joules. Now, how do you find the force of friction? Well, you just said work done by friction equals the force of friction, the distance of the ramp, or the length of the ramp, cosine of 180. Okay, so this is going to be negative 5096 equals the force of friction times 2.8 times negative 1. And you can figure out that the force of friction is 1,820 newtons. All right, let's look at number 30. A block of mass 750 grams, so you have to be careful to change that to kilograms, is released from rest and slides down a frictionless track of height 52.2 centimeters. So you have to change that to meters. At the bottom of the track, the block slides along a frictionless horizontal table until it hits a spring attached to a heavy wall, blah, blah. The spring is compressed that much, okay? That's the maximum compression, meaning like at that moment, it has no kinetic energy, so it's gonna start to go back. What is the K value for the spring? So we're looking for the spring constant. So basically, this is what we're looking at. Okay, here's a wall, here's a spring. So you let something go down here, block, I guess, slide in. It's gonna hit it, compress it, okay, to here maybe, and stops. So we need to figure out, stops and then bounces back. Okay. So I think the way we should do this is like say, well, I'm going to look at this as my initial state, and my final state is when the spring is fully compressed. And there is no friction between these 2 points here. So I'm going to say the energy at the top here, right, has to be equal to the energy down here. So the energy at the top here is in the form of gravitational potential energy. Okay, so that's what my equation should look like. There is no work in between. So let's look at the, and again, I'm going to choose my system as the spring, the block, and earth, just to make it simple. I don't want to deal with work done by gravity and work done by the spring and all that stuff. All right, so this is going to be mgh, so 0.750 times 10, and the height is 0.552. And that's equal to 1/2 k x squared, which is 0.0264, and we have to square that. So now, if you do the math correctly here, you should get 11,880 point something, 0.17, and the units for K, the spring constant, is newtons per meter. And the reason for that is F equals Kx. Okay, don't confuse this K with kinetic energy. So if you want to find the units for anything, you just isolate it. So F is in newtons, X is in meters, so it's got to be newtons per meters. Meaning this is a very, very, very stiff spring. In order to stretch it 1 meter, you have to hang almost 1,200 kilograms on it. So 1 meter to stretch it by about this much, right? I don't know, you can probably see it. You need to put this much mass on it. And just guessing, that's probably about 2,500 pounds. So it's very stiff. Okay, now let's look at 31. If I raise a 0.5 meter pendulum 0.25 meters from its starting resting position, what is the maximum velocity? What will the maximum velocity be, and where will it occur? Well, so here's the pendulum. You're going to raise it to here. I'm going to exaggerate this picture. Okay. So this height here is 0.25 meters. Now the maximum velocity will happen at this level here when it's vertical, and the reason for that, because all the energy, all the potential energy you had up here is converted into kinetic energy. If we look at this level here as 0, gravitational potential energy, all your energy is in the form of kinetic energy, which means you got to be going the fastest when you're down there. All right, so let's see if we can figure out the speed. At this level here, I only have mgh. Down here, I only have 1/2 mv squared. And assuming that there is no friction between those two states, between the initial and the final state, I think we can set this equal. And if we set them equal, we get v equals radical 2gh, which is 20 times, what is it? 2 times 10 times 0.25. Okay, so this is going to be radical 5, it looks like. Okay, that's 2.24. All right, let's look at number 32. Okay, this time it's a little different. So they're giving us an angle this time. Okay, so this angle here is 35 degrees. Okay, how high above its resting position did it rise? All right, so I think we can figure out the height. So instead of finding the height here, I'm going to find it here. Okay, and basically the way I'm going to do it is that I'm going to take the length of the string and subtract this piece here, which I can find inside this triangle here. Okay, so you can see clearly that this length here is L also, right? This is going to be L cosine of 35, right? So basically this height is going to be L minus L cosine of whatever that angle is usually, right? That's what it's going to be. So the height is just going to end up being, I can probably factor out the L, and we should get 0.054 meters. So 5.4 centimeters. Okay. What will its maximum velocity be? Well, the maximum velocity is going to be down here. So at this level here, all the gravitational potential energy I had up here becomes kinetic down there. So I can write, I'll write it here. mgh equals 1/2 mv squared. So I'm doing the energy initial plus work done in between the two states equals energy final. So the mass is not important. So the g, and if you remember when we did the law of inertia, when we talked about Galileo's experiment, we put heavy marbles and light marbles, and you can see that the period was the same. Okay. So V equals radical 2gh. And you can do the math and get a value of 1.04 meters per second. Okay. A 2-kilogram bowling ball is attached to the ceiling by a 3-meter long string. The bowling ball is pulled aside so that it rises 0.12 meters vertically. So they already given us the height. Calculate the gravitational potential energy at this height. So that should be easy. It's mgh, which is 20 times 0.12. What is that? 2.4, I guess? Yeah, 2.4 joules. Yep. Okay, what is the kinetic energy at the bottom? Well, all this energy, all these 2.4 joules gets converted into kinetic energy at the bottom. So that's the K at the bottom. Okay. Now we need to find the speed. So we're going to write K is half mv squared. So 2.4 is half. The mass is 2 v squared. So v is radical 2.4, which is 1.55 meters per second. All right. Number 34. A simple pendulum has a length of 0.75 meters and a bob. The bob is basically what's attached to the bottom of the pendulum, to the string. And a bob whose mass is 0.15 kilograms. The bob is released from an angle of 25 degrees. So this angle here is 25 degrees. Okay. This length here is 0.75 meters. That's the same thing here. I'm going to pick this point here as my reference for gravitational potential energy. What is the vertical height of the bob when released? So I think I can figure out this height by doing what I did in the previous problems. It's just going to be 0.75 minus 0.75 cosine of 25 degrees. All right, so you find in this length here, which is basically this whole thing, minus just that. And to find this piece here, you would work inside this triangle here. I hope you can see that. Okay, so that's going to be 0.070. Okay? All right. What is the kinetic energy of the bob when the string is at an angle of 9 degrees? Okay. So basically this gets to this level. This angle here is 9 degrees. Yeah. Okay. So I think I'm going to pick this point here as my initial state and this point here as my final state. Okay. So I can say that the energy at the initial state plus any work done between these two states, which is 0, equals the energy at this level here. Just keep in mind that when you are at an angle of 9 degrees, you have both kinetic energy and gravitational potential energy. So just be aware of that. So when I'm at the initial state here, all my energy is in the form of gravitational energy, potential energy. And when you are at this location here, you have both gravitational and kinetic, which is important. Okay. So if you want to find the kinetic energy, you have to find the difference between these two. So this is going to be mg. This h, 0.07 minus mg. Now to find this other height here, to find this height, it's just going to be 0.75 minus 0.75 cosine of 9 degrees this time. Okay, so it's going to be mg, and that's 0.0092 equals K final. And that should give us a value of 0.091 joules. Okay. What is the speed of the bob at the bottom of the swing, meaning like at the very bottom here? So at the very bottom, this equation changes to become like that. Okay. So basically, this term is no longer there. Okay. And this K final becomes 1/2 mv squared. So I think we can get rid of the divide by the mass. So I don't think we use the mass at all for this whole thing. Each time we had it, we crossed it out. Yeah. Actually, we only used it to find the difference in gravitational potential energy. All right. So this is going to be 0.7 times 2, so what is that? 1.4. So V is radical 1.4 meters per second, which is 1.18 meters per second. All right, let's look at number 35. Okay, a pendulum is suspended on an 87 centimeter length of rope. If the pendulum is pulled back to an angle of 37 degrees with the vertical, what is the speed at the lowest point? So I'm going to go quick with this one because we just did something similar to it before. So this angle is 37 degrees. You just have to pay attention to the units here. Okay, if they don't give you the mass, it's most likely going to cross out somewhere. So we need to figure out this height here, which I showed you is the length of the string, okay, minus the length of the string cosine of 37. Now you could have found this in centimeters and change it later. You can change the length to meters right away. You do whatever works for you. So the height is 0.175. meters. Yep. Now, if I choose this as my initial state, this is my final state. UG at the top here equals the kinetic energy at the bottom down here. So this is going to be just mgh equals 1/2 mv squared at the bottom. So I can divide by the mass. So 1.75 times 2, I think that's 3.5, and we take the radical of that to get the V. So the V is 1.87 meters per second. Okay. A mass slides 12 meters along a frictionless inclined plane. It starts from rest at a height of 7 meters. What is the speed when it reaches the bottom? Now, this is frictionless, okay? So we start here. We slide in down the ramp. We don't know this angle, but we know the height is 7 meters. That's all we care about, okay? And it doesn't tell us the mass, so it's going to cross out somewhere. I'm going to look at this as my initial state, the bottom of the ramp as my final state. Okay. So I'm going to say, well, the gravitational potential energy at the very top, right, has to be equal to the kinetic energy at the very bottom. And the reason for that is because there is no friction in between. If you had friction, you will add the work done by friction here. So this is just going to be mgh equals 1/2 mv squared. So you divide by m. So V is going to be equal to radical. Looks like 140. So it should be about 12. And it is. It's about 11.83 because radical 144 is 12. All right. Okay. 36. A rock is on the edge of a 100-meter cliff. The rock falls from the cliff. What is the speed just before it strikes the ground? So assuming it starts from rest here, so someone drops it or it just falls, okay, because it's on the edge, so there's no initial speed. So here's the cliff, here's the rock, and it's going to reach down here. So I'm going to use this as my reference for gravitational potential energy. Okay, so when I'm up here, this is my initial state, this is my final state. I only have gravitational potential energy. Here I only have kinetic, and it doesn't say anything about friction, so we're going to assume a frictionless environment. In the textbook and in the take-home quizzes, you have problems like this where there is friction, there is air resistance. Okay, so mgh is 1/2 mv squared. That's basically coming from this equation. If someone throws this or pushes it to something, you have to take into account its kinetic energy up there. So we divide everything by the mass. So G times H, so that's going to be 1,000. Okay, times 2, so it becomes 2,000. Take the square root, and that's your velocity. And that should be about 44.72 meters per second. Okay. All right, number 38. Okay. Janet jumps off a bridge with a bungee cord tied around her ankle. So here's the bridge. She's standing here. Okay, something is tied to her ankle. She falls for 15 meters before the cord begins to stretch. So in other words, for those 15 meters, there is no gravitational, there is no elastic potential energy. So we're going to treat this cord as a spring. It follows Hooke's law, right? And it says that in here. How far below the bridge will Janet fall before coming to a stop? So we're going to look at this two ways. So when she's here, right, that's when the cord starts to stretch. And when she's down here, the cord stretch an amount x here, right? So I'm going to look at this lowest point here as my final state, and I'm going to look at this point here as my initial. And I'm going to see what we can do here. So at this level here, all my energy, and by the way, and this is 15 meters. Yeah. Okay, that's the length of the rope before it starts to stretch. Okay, so it's going to be UG at the top equals, now let's think about what we have at the very bottom. So here I'm going to look at this as my zero, my reference point for gravitational and potential energy, equals energy stored in the spring at the very bottom. So at the top, she has m, g. The height from this level is basically 15 plus the amount of stretch. And that should equal to the energy stored in the spring, 1/2 k x squared. Now to solve this, you're going to need to use your calculator or do a quadratic equation, and you should get an x equal to 41 meters. And to figure out how high above the this point she is, right, you just have to add 15 to 41, because this is 41. So you have to add the 15 to it.